Okay, so we'll assume with SVD, okay, SVD and then positive definite matrices quadratic forms. Those two quickly we'll wrap up those two. Okay, so this is, yeah, you can hear me, right? Oh, okay, so SVD is where we start. So there are we have seen spectral decomposition. So that is one kind of matrix decomposition. What we have now is something much more powerful. It is not just for any square matrix. So spectral decomposition, eigen decomposition, all these things are for square matrices, right? Spectral decomposition, in fact, is for square Hermitian matrices only, or squares real symmetric. But then SVD is a decomposition for any m cross n matrix, right? It's not necessarily square. So the way to understand SVD is to go through two matrices, A transpose A and A transpose. Okay, so these are very, very important matrices. And half of SVD will become quite simple if we know what these two matrices are. Okay. So given A, M cross N, A transpose A is N cross N, A transpose is M cross M. So this should be clear enough. So what are the properties? So there are some properties. Once again, I will list down the properties. I'll give the proofs in the PDF. You can look at them later. Okay. So the first thing is A transpose A and A transpose are symmetric. So that is very convenient because you can bring in the whole spectral theorem here, right? The real version. So A transpose A are orthogonally diagonalizable, right? So that all those things follow. So that is why this property is important. So I'll also tell why each of these properties are important. So this being symmetric allows us to do QDQ transpose, right? So that is the main advantage of this. So proof is very simple. This is straightforward, right? So the transpose you take, you equate it, you obviously see that this is the original matrix. Okay. So the next one is again a very important property. The fact that the eigenvalues of A transpose A and A transpose, they are positive, or not, rather they are non-negative, right? So they can never be negative. They could be zero or they could be positive. Okay. So this is also very useful. So can someone tell me where this property will become useful? Do you see in SVD, where is this property used? The fact that they are non-negative.
While calculating the singular value, we do square root of
Exactly.
lambda.
Very good. Yeah. So that is where it is useful, right? So the singular values are nothing but square roots of the eigenvalues of A transpose A or A transpose, right? So it is necessary that they be non-negative, right? Otherwise, you can't even define that. So this is used where in calculating the singular values, right? Or rather, it is because they are non-negative that we can calculate the singular values. Okay. So that is the property. Again, some proof for that. So this is again another useful property. The A transpose A and A transpose are not just having positive or non-negative eigenvalues, they have the same positive eigenvalues, right? So the reason they are, we call them non-zero, right? The reason there is non-zero is because these are two different dimension matrices, right? So A transpose A is n cross n, this is m cross m. So this will have n eigenvalues, this will have m eigenvalues. So n is not equal to m in general, right? So there is no need for them to have exactly the same number of eigenvalues. But then we can surely say that they have the same positive eigenvalues. So for example, so what does that mean? It means the following: if you have let's say A transpose A is, let's say A is 3 cross 5, then A transpose A is 5 cross 5, right? A transpose A is 5 cross 5, and A transpose is 3 cross 3, right? That's it. So if A transpose A has the eigenvalues, let's say, I'm just randomly making things up. So let's say 3, 2, 1, 0, 0. What can you say about the eigenvalues of A transpose?
3, 2, 1.
3, 2, 1. Okay, because of the result that we just saw. 3, 2, 1. There are 3 positive eigenvalues. A transpose also has to have exactly those 3 positive eigenvalues, right? In fact, this is true up to multiplicity also. For example, if these are the eigenvalues of A transpose A, then the eigenvalues of A transpose are 3, 3, 1. So when we say positive eigenvalues, we don't just mean the unique values, right? We mean up to multiplicity. So meaning if 3 is repeated 2 times here, then 3 has to be repeated 2 times here. Okay, no escaping that. So that is what we mean by positive eigenvalue. So if this is 0, for example, what will change? A transpose will have
330.
yeah 330, right? So one of them will be 0. So this is why the theorem, or rather the property, is telling us that they have the same positive eigenvalues, but not all eigenvalues are the same. Meaning this has 5, but this has only 3. So the number of 0 eigenvalues is going to be different. So that's what the properties. That's how you should understand the property. Okay. So they have the same positive eigenvalues or the same non-zero eigenvalues. The last part is regarding the rank. Okay, so can someone tell me where the rank will come in SVD? Do you know where rank plays a role?
After reducing the rows.
Okay, that is finding the rank. I'm asking about where this property is going to be useful in SVD.
Finding independent eigenvectors.
Okay, finding independent eigenvectors. All right, there is actually one place. There is what can you say about the rank of a matrix and the number of eigenvalues? Can you say anything?
So same.
They should have
Okay.
same.
So they are not exactly the same, right? So see the rank.
They are, if rank is R, then they have R similar eigenvalues.
Okay, there are R positive singular values, right? So the rank plays a role in the positive eigenvalues, right? So there are
Yes.
as many positive eigenvalues as the rank of the matrix. Okay, so
Like the number of ranks is equal to number of eigenvalues.
singular values, right? So did I
Okay.
say eigenvalues? So if I had said eigenvalues, I'm wrong. So it's singular values, right? So if there are, for example, once again, these are all we have to we haven't discussed the proof, but I hope this is clear enough. So for example, if you have a matrix like this, right, 3 cross 5, and you are given the rank of A to be, let's say, so what is the maximum rank that A can have?
3.
3, right? So maximum rank can be 3. Let's say the rank in this case is 2. So what you can say without even batting an eyelid is that sigma 1, which is the first singular value, is greater than 0 for sure. You can say that. Sigma 2 also is greater than 0. You can say that for sure. In fact, you can say that sigma 1 greater than sigma, or greater than or equal to. We don't know if they are equal. They could be equal. But you can say this for sure. Okay. So there are as many positive singular values as the rank of the matrix. Okay. And it turns out that rank of A is the same as rank of A transpose A and A transpose. So that is why you can actually argue all these things. Okay. So sorry for not discussing the proofs now, but you can always, this is actually slightly involved. So you have to argue, bring in concepts like null space and all that. That's why I have not put them in, I put them in gray because it's slightly involved. So if you're not able to understand it later on, you shouldn't worry. Okay. So this is like, some proofs are extra reading material for those who are interested in completeness. Okay. So these are the 4 properties you have to memorize, commit to memory, but don't mug up, right? So by memorize, I mean you have to put it in your long-term memory. So I don't mean memorize in the sense of, uh, so mug up and then vomit, right? So that's not the way I'm asking you to do it. So just understand what is behind each of these properties. Okay. So I'll just repeat. This is self-evident. The eigenvalues are non-negative will be used when you take square root of eigenvalues, right, to get singular values. So they have the same non-zero eigenvalues. Did I say why that is important? Okay, so this is kind of used in the proof elsewhere, but this rank part is important because that will tell you the number of positive singular values. Okay. So these are the 4 properties. Any questions in this case, in this slide? No, right? Okay. So then we go to the statement of SVD again without proof. So every real matrix, so we are only looking at real matrix. There is a corresponding version for complex matrix where you replace U with U star, sorry, U with unitary. So orthogonal will become unitary and diagonal will remain the same. And this will become U sigma V star. Okay. So the complex version is there, but for our course, we'll focus mainly on the real version. Okay. So every real matrix, no matter whether it's square, rectangular, whatever, it is going to have a decomposition. So the reason it's called a decomposition is because you're breaking it down into the product of 3 matrices. Okay. So U is orthogonal, meaning the columns of U are orthonormal. The columns of V are orthonormal. And sigma is diagonalish, meaning it is not necessarily diagonal. So it need not be square. So it's M cross N. But then all the entries on the main diagonal are what we care about. Okay, so rest of them are 0 for sure. The entries on the main diagonal may or may not be 0. Is this part clear? What we mean by diagonalish matrix? Okay. All right, so that is the statement. So there are 3 singular things here. Okay, so when we say singular, the singular is actually an adjective for 3 things. So you must know all 3. Okay, this is a part of the course. Yeah, I'm not telling you something extra. So you have to, I don't know if this was discussed in the lecture, but this is a part of the course. So there are what are called singular vectors. Singular values you already know, sigma 1 to sigma whatever, right? So that you're familiar with. But singular vectors, there are 2 kinds. Whatever goes into U and V are called singular vectors. Now, depending on which one it goes into, they are either called left or right singular vectors. Okay, so let's first take U. So U already, as we already know, is orthogonal, right? So U transpose U I, that is there. Now, every one of these columns, right, is called a left singular vector. Okay, so why is it called left? Because for the simple reason that it appears on the left. Okay, so it's a left singular vector. Now, what do you think V is going to be? V is going to contain the right singular, right? Yeah, so right singular vector. So every Vi is a right singular vector. So, but what goes in here is of course V transpose, but still, so every Vi is right singular vector. And what is there in the middle are the singular values. So there are these diagonal entries are the singular values. Now there are at most these many singular values. Okay. So what do I mean by that? Once again, we discussed this earlier in an earlier session, but I'll just add this. So let's take this example again, right? So if you have 3 cross 5 matrix, okay? So the singular sigma matrix is of dimension. What is the dimension of sigma?
3 cross 5.
This is also 3 cross 5, right? So therefore, you can, the number of diagonal entries, right? How many diagonal entries can this have?
Minimum of 3, 5.
Yeah, minimum of 3, 5, right? So if you're not able to see that, so this is 3 cross 5, right? So this is 1, 2, 3, 4, 5, right? So notice that this is like a wide matrix, right? So if you start with sigma 1, this is sigma 2, okay? This is sigma 3. So you can have 3 singular values here at most, okay? You will have rather, okay? You will have 3 singular values. Now, which of them will be positive? So out of sigma 1, sigma 2, sigma 3, how do you know where the positive singular values will stop?
So up to sigma 3.
How do you know that? So why can't it stop at sigma 2? So this is what we discussed earlier, right? There is some quantity which will tell you which is the last positive singular value. Rank, right? So if the rank is 2, for example, then sigma 1, then what you can say is sigma 1.
Sigma 2, up to sigma 2, it will be positive.
Yeah, it will be positive. And then, so this will be 0. Sigma 3 will be 0. Okay, so this is one example. Now, let's take another 5 cross 3, for example, right? So another example would be 5 cross 3. In this case, sigma will become what?
5 cross 3.
5 cross 3, right? So
5
there'll
cross.
be, so how many sigmas will be there on the diagonal?
3, sir.
once
3.
again 3, right? So once again 3. So that is the, so this is 3. This goes below. So this is 5 cross 3, right? So notice that once again you are left with only 3 on the diagonal. So you can have at most 3 singular values. So whether it's 5 cross 3 or 3 cross 5, you can have only at 3 singular values. Therefore, in general, so the number of singular values can be minimum of, right, at most, or rather not at most, exactly m comma n. Okay, so I'll just repeat this. So if a matrix A has shape m cross n, it will have exactly minimum of m comma n singular values, right? This is guaranteed. Okay, out of this R, okay, of them will be positive, where R is
Rank of the matrix.
rank of the matrix, right? So this is the complete understanding of singular values that you must have, at least the sigma matrix. Okay, is this clear to everyone? What we just discussed? Okay, right. So these are the singular values, and then this is what we were just discussing, right? So sigma 1 to sigma r are positive. Sigma r plus 1 to sigma minimum of m comma n will be 0. Okay. So that is singular things. So singular vectors left and right, and then singular values. Okay. So once that is done, you have properties. So you have like 3-4 properties which are very important. So, and that is what in fact is used to even derive the SVD. Okay. So the first property is the left singular vectors, right, are the eigenvectors of AA transpose. Okay. So remember, AA transpose is m cross m, and the left singular vectors are inside U, right? U is always on the left. So U is m cross m, right? So you can kind of make that connection. So left singular vectors are eigenvectors of AA transpose. Now, from where does this orthonormal come? How can you say that it's orthonormal?
U star U equals to
U is a symmetric matrix.
Yeah, U is symmetric or it's orthogonal, right?
Yeah, orthogonal.
You meant orthogonal. Okay, so
Yes.
U is orthogonal. Therefore, the columns of U are orthonormal vectors, and they are all eigenvectors of AA transpose. Okay. Similarly, what can you say about A transpose A? What will be the eigenvectors of A transpose A?
So it should be similar because A transpose A equal to AA transpose.
No, they are not equal, right? So they only have the same positive eigenvalues, right? They are not. They are of. In fact, they have different dimensions, right? One is maybe 3 cross 3, another one is 5 cross 5.
Okay.
A transpose A is symmetric, hence their eigenvectors will be orthogonal.
A transpose, that is correct, but can you like extend this idea to A transpose A? If the left singular vectors are orthonormal eigenvectors of A transpose, what can you say about A transpose A?
So since A transpose is similar to A transpose A.
That is right. Yeah, they are related, but what I'm asking is if
They're
you are
right singular values.
the right singular vectors are the orthonormal eigenvectors of A transpose A.
Yes, sir. Yes, sir.
Right. So this is the connection. So on the left you have eigenvectors of A transpose. On the right you have the eigenvectors of A transpose A. Okay, this is the connection. So in fact, you will use one of these two to derive the SVD, right? If you think about it, we'll come to that, but you must have done this quite a few times, right? You either take A transpose, diagonalize it, and then find the singular vectors, or you take A transpose A. So in one case, you will arrive at the left singular vectors. In the other case, you will arrive at the right singular vectors. Okay, these are two very, very important properties because deriving the SVD is itself dependent on this. Okay, so that is that. Now, this we already saw. The positive singular values are the square roots of the positive eigenvalues of A transpose A. That's how you get the singular values. And there are R such positive singular values. Okay, so these are the four properties. In fact, all of them can be, it will become very clear why they are true if you look at the SVD of A and compute A transpose and A transpose A. So if you take SVD of A, right? So SVD of A is what? U sigma V transpose. So if you look at A transpose, it is nothing but this into this, right? This is A transpose. So U, some diagonal matrix U transpose. V, some diagonal matrix V transpose. So what is this for a symmetric matrix? What can you say? What is this called? Something into
Antimatrix.
no, right? So, sorry.
It is orthogonally diagonalized.
Yeah. So this is the orthogonally diagonalized. So this is the spectral decomposition, right? Whatever we saw as spectral decomposition, that is this. So this is okay. So instead of unitarily diagonalizable, it's orthogonally diagonalizable because these are orthogonal matrices. Okay. So this is where it comes from. Okay. So U, for example, will contain the eigenvectors of A transpose. So these are nothing but left singular vectors. V will contain the eigenvectors of A transpose A, and V will have the right singular vector. So that is how these properties are actually derived. Okay, any questions on this slide? Okay, so that is SVD properties. So other important thing, very important thing is to understand the relationship between SVD and the fundamental subspaces, right? So we saw the fundamental subspaces in week 3. So the SVD can directly give you the 4 fundamental subspaces. So this is, for that you need to understand this. So have you seen this before? This particular form of the SVD?
Yes, sir.
You have seen, right? Okay. So this is a very, very important form because this is this will help you understand several properties of what we are going to discuss, right? So see, what is this actually? This is just an expansion of this singular value decomposition in terms of R matrices. So each one here is a matrix. So UV transpose is a matrix. So there are R such matrices. So these are all, what is the rank of each matrix? This we discussed before.
1.
1. Okay, each one is a matrix of rank 1. In fact, in this case, what happens is each matrix is of rank 1. So if you sum all these, you get a rank R matrix, which is A. Okay.
At most R.
Yeah, at most R. In this case, exactly R. So you here rank of A is equal to R, and you have expressed A as the sum of R rank 1 matrices. Okay, where each matrix has a singular left singular vector sitting here and a right singular vector sitting here and the corresponding singular value. So it's a very, very important decomposition. Okay, this is the SVD, but then not expressed in terms of this nice form, slightly different. Okay, so if you multiply A with VI, what will you get? A into VI.
So A is equal to summation of sigma I ui vi transpose.
Correct. So what I'm asking is, if you multiply A and VI, so one of these V's, what will be the output? Say you multiply V1, right? So A times V1, what is V1? What is AV1?
So V1 and V1 transpose will now
Identity, and we left with rho 1 V1, I think. Rho 1 U1.
Yeah, sigma 1 U1, right? So
Yes,
Yes.
sir, sigma 1.
so is this
and
clear?
A also we have.
Yeah. So is this clear to you all? So what I've written here, AVI is sigma I UI.
Yes, sir.
Okay. So why is this equation important?
So, but in right hand side, there should be A also, right? Because we are multiplying A, VI both side or only VI both side.
VI, right? So you are multiplying by
Okay.
VI here. So what happens is VI transpose VJ is 0
Yes,
for all the
yes.
others and only this.
Sigma I UI, yes.
Okay, so why is this important? Or what does this remind you of?
We can just calculate vi, and then rather than doing a transpose, we can derive u from here.
Correct, that is good. So that is one use of this equation. Does this remind you of anything else? So for square matrices, AV is equal to lambda V, right? So, but for a rectangular matrix in general, you don't have eigenvalues. So but then you have singular value. So this is something like A into something equal to sigma into something else. Okay, so this is kind of an extension of eigenvector, eigenvalue, that idea to a general rectangular matrix, right? So this is AV equal to sigma U. Only thing is that these are not eigenvalues, but singular values, and these are not eigenvectors, but singular vectors. Okay, so that is how you have to look at this equation. So this equation is not something that is totally new. You can think of this as an extension of eigenvalue, eigenvector business. Okay. So likewise, if you for A transpose, can you express A transpose like something like this using a sum like this? A transpose equal to what?
We will transpose of the expression, transpose this expression.
Correct. Yeah, that is correct. Of course, that is true. But then what will that turn out to be?
Sigma will remain the same, and U transpose and V1
VI UI transpose sigma.
U1,
Yeah.
yeah,
That's correct. So it will be sigma 1 V1 U1 transpose, right? So just
yes, yes,
usual
sir.
rules, right? So AB
Yes,
transpose is
sir.
V transpose A transpose. So this becomes V1 transpose transpose, right? So it's V1 U1 transpose. Order changes. Therefore, A transpose UI is equal to what? If you multiply both sides by U1, let's say, what will
Yes,
you
sir.
get?
Rho 1,
Sigma I vi.
Yeah, sigma I VI. Right? So this is the contrasting equation.
yes, sir.
So this you will use one of these. So if you start with A transpose A, you'll have to use one of them. If you start with A transpose, you'll have to use the other one. Okay. So that's the whole point. So these two equations are going to help you in finding out the left singular vector or right singular vector when you have the other one. Okay. So that is with respect to the two equations. These two are extremely important. Okay. So once you have this, you can discuss the four fundamental subspaces. Okay. There are four spaces you already know: row space, column space, null space, left null space, right? So RM, so RM will have two subspaces. What are the two subspaces that will sit inside RM? Column space, row space, null space. Which of them will go into RM? The left hand side.
column space, sir.
Okay, column space and
Left
Null.
null space.
yeah, correct. Left null space, right? So you'll have
Left null space, sir.
column space and you'll have the left null space. Okay, what is column space? You can see that A times V, right? So that will be the so you'll get all columns using AVI. So they're all just linear combinations of these UIs. So U1 to UR. So the first R singular vectors, left singular vectors, span the column space. The remaining vectors span the left null space. So you can see what will happen here, right? If you multiply A transpose with U R plus 1 and so on, you will get 0. So that's why it's in the null space of A transpose. Okay, so what is remaining here?
Yes, sir. Row space.
Column null space.
The null space, right? So these two are remaining. So row space and the null space, and notice that these are perpendicular. So you must know that. So these two are perpendicular. These two are perpendicular because you can see that this is orthonormal, right? So u1 to ur will, all of them are perpendicular to ur plus 1 to ur, right? So this is like a fundamental result in linear algebra. So in fact, Professor Gilbert Strang calls this the fundamental theorem of linear algebra, okay, because it's very important. So once you understand the SVD, you can connect it to the four fundamental subspaces. You can, in fact, also connect it to least squares, which we studied, but we can't do it now. We don't have time. But you can, like, once you have the SVD, you can do so many things, right? So this is a very important slide for that reason. So these are all subspaces. So each one is a subspace. So that is regarding fundamental subspaces. Okay. So next one example. So this example again, I won't work it out. You can work it out later. So if you have a matrix like this, so what are the steps that you follow? What is the first step? You start with,
Compute A transpose A or
yeah, you compute A transpose A or A transpose, right? So depending on the size of, on the shape of the matrix, you will either go for A transpose A or A transpose. So let's, in this case, let's start with A transpose A. So that will be step one. Step two will be, what will be step two?
computing eigenvalues.
Eigenvalues, eigenvectors, right? So in this case, they turn out to be nice, distinct eigenvalues. So your task is made simpler because each one will return exactly one linearly independent eigenvector. So next, what you do is so in this case, they are the right singular vectors, right? So these are the V's. So remember, A transpose A is n cross n. So you will get the right singular vectors, or the V1, V2, V3. So these are three vectors. So you can, these are nothing but the eigenvectors of A transpose A. Okay.
So after finding the eigenvectors, you normalized all the
Yeah,
eigenvectors.
yeah, all of them. These are all normalized vectors. That's why they are singular vectors, right? So they are, all of them are normalized. Yeah. First find the eigenvectors, then normalize to get the right singular vectors. So then you get the singular values, which are the square roots of the eigenvalues. So root lambda 1, root lambda 2, root lambda 3. Then you do, what do you do next? Once you have right, you should compute the left singular vectors, right? So what equation do you use here to compute u1 and u2?
Sigma I ui is equal to 8 times vi.
Yeah, exactly. So AV by sigma, right? So AV by sigma will give you u1 and u2 directly. U3 is a slight tricky business. We did this exact example in the live session few weeks back, right? So you will have to find a way to, you'll have to get a vector that is orthonormal to 1, 0, 1 and 1, 1 minus 1. Here it's easy. You just need to eyeball and you can figure out something like this. If not, you'll have to solve a system of equations. Okay, so this part, is it clear or is it?
Actually, fourth step I just didn't get.
This is singular values, right? They are the square roots of the eigenvalues of A transpose A. By definition, that is the singular values, right? Root of lambda 1, right? Root lambda I have just used the definition of what a singular value is.
So how you get these values?
By taking the square root. Here, right? So the step 2 to step 4, there is a link.
Oh, okay, yes.
Okay, so step 5, is it clear to everyone how we find out U3? U3, you need to assume it has some vector ABC, and then you have to show that this vector is perpendicular to U1 and U2, right? So we did this. For those who are not clear, please refer to a week 6 live session where we have done this. Okay, so that's left singular vectors and that's all. So once you have this, you just need to put all of them together into U. So U sigma V. Okay, so that's your SVD. So usually in the exam, we will make sure that you don't have to, break your head over finding these U1, U2, U3 so it requires a bit of computation and careful number crunching, right? So there are two difficulties you might face. One is if the lambdas are equal, then you'll have a bit of a problem. Why would you have a problem if lambdas are equal? Can someone tell me that? For example, if all these lambdas turned out to be 4, what issue will you face?
So vector 2 will be vectors, finding vectors will be problemsome.
So you will be able to find vectors, but then they don't necessarily need to be what?
Linearly
Independent.
Correct. Linearly independent is a problem, but more.
They are not diagonalizable.
So the vectors
They
need not be
cannot be
orthogonal.
diagonal.
So you, yeah, both are problems. So you may not be able to find independent vectors, but more importantly, what we want is orthogonal vectors, right? So finding orthogonal vectors will be hard. Okay, so if all three eigenvalues are same, finding orthogonal eigenvectors is not impossible. Of course, you can do it because you are guaranteed to find them, but it is hard. How do we escape that fate in this case?
We have to do Gram-Schmidt.
Right, in that case, but how do we escape this problem here? How come that they are all in orthogonal here? Are we
distinct
lucky?
eigenvalues.
So we can apply formula v1 dot v2 is equal to the value is equal to 0. So by
Yeah.
applying that we can do it.
No. So that is not the question I asked. So the question is, how come they turn out to be orthogonal in this case? The reason is you have
Symmetric matrix.
symmetric matrix and distinct eigenvalues, right? So that's why they turn out to be orthogonal.
Yes.
Okay. If they are, so the question I was asking is, if they are all equal, what do you do? That is when you have a problem. But yeah, so assume that mostly we won't ask questions where you have to, break your head to find orthogonal eigenvectors. So that is a bit of work. Yeah.
One
Go on.
doubt, are we guaranteed if the eigenvalues are equal, say for example 4, 4, 4 like that, then even that should be the same with the nullity, right? Like the geometric multiplicity should be equal to algebraic multiplicity, right?
Correct.
Are we guaranteed that will always happen for a symmetric matrix?
Yeah, so symmetric, see the geometric multiplicity and algebraic multiplicity are equal for diagonalizable matrices. So that is one property of any diagonalizable matrix. So if you have a symmetric matrix, it is by the theorem, spectral theorem, it is diagonalizable, right? So therefore, it will have equal multiplicities.
Okay, then we are guaranteed to find the basis for null space, right?
Exactly. You mean basis for Rn?
Yeah.
Yeah. You are guaranteed. So you mean null space of A minus lambda I, right?
Yeah, correct.
Yeah. You are guaranteed to find the basis. The only thing is, it won't be so straightforward as this, right? It won't come and fall into your lap. That is what I'm trying to say.
Okay.
You'll have to spend some effort finding out independent eigenvectors, but it is guaranteed. So you are guaranteed to find them, but it is going to be slightly harder, is what I'm saying.
Okay, got it.
Okay, so for the exam, you can rest assured that you will mostly be given, distinct eigenvalues. The other problem is interesting. So what happens if they are equal? Maybe when we have more time, we'll discuss that. Okay,
So,
yeah.
like, so please open the last page. Like we found v1 and u1, all vi's and ui's. How you put the values in the matrix form?
That you just plug in u1, right? U1 into the first column, u2 into the
Yes.
second column, u3 into the third column. So we are just taking the √6 common.
But like u1 we have 1 by √2.
Yeah.
1,
So this
0, 1.
Yeah, we did know in that week-6 session. We are taking 1 by √6 outside. So
Yes.
this will be √3 by √6 is √2. √3 by √6 is √2. So you will get the same thing.
Okay.
Right? So, okay. Yeah. So finally, this low rank approximation, right? So this is the last slide in this VD. So you have some questions have been asked in the past. So in the mock also, there is one question. So what is the best rank k approximation of A. So first of all, you have to understand what best means, and that will require us to define what is called a matrix norm and all that. So we haven't done that in our course. So I'll just tell you what to do in this case. Why this makes sense, we'll have to discuss this later. Okay, so what should you do if you're asked the best rank k approximation? You have to truncate the SVD after k terms. Okay, so if, for example, if you're asked the best rank 1 approximation of A, you just have to compute this quantity. Sigma 1 U1 V1 transpose is the best rank 1 approximation of A. Okay, so is this clear? So I know I haven't told you what best means, but for now, just take this for what it is. We will, in case you get a question like this, you have to compute this best rank 1 approximation is sigma 1 U1 V1 transpose. All right, so is this clear to everyone? Okay, so that brings us to the last part, which is quadratic forms and definiteness, right? So this is so I'll just give you a small motivation as to why we are studying what we are studying in this part of the course. Okay, so if you have f in R from R to R, right, some function, and week 8 onwards is anyway optimization, right? So if you want to minimize, or if you want to find the minimum local minima of f, what would you do? What would be the first step you would do?
So differentiate with respect to the variable.
Okay, and then
Equated to 0.
okay, what will you get in the process?
The derivative
Minima
Critical.
or
Minimum.
Critical.
minima or maxima.
Okay, critical points, right? Not exactly, not directly minima and maxima. So you will first get what are called the critical points of f. In fact, stationary points, to be very precise.
Yes.
But critical points also involve points where the function is
So
Not-
no, saddle point, I think.
Yeah.
not differentiable, right? So see, critical points are two in nature. So they could either be points where the function is not differentiable, or where the derivative is 0, right? So that is what it means for a point to be a critical point. For our course, assume that there will be, we're all the differentiable functions, right? So we can forget that part. So wherever the derivative is 0, that is where those points are what are critical points. So that is one step. Find critical points. So you have to solve f dash of x equal to 0. How do you know from the points that you have, how do you determine if a point is maxima or minima?
So second derivative, take the second derivative, and if it is less than 0, then it is maxima, and if it is greater than 0, then it is minimum.
Correct. Yeah, you do the second derivative test. So I think I have interchanged the maximum and minimum, right? Yeah, I have to change this. This is wrong, no? This is
Yes, sir.
it is greater than 0. It is
Yeah, 0 minima, and less than 0 is maximum.
okay. Once again, I will forget. Otherwise, this will go as being streamed. So let me better change it now itself. So then I have to change it on 4 slides. Okay, so this is like, I hope whoever is seeing this later will make a note. Okay, so this is a mistake. I'll update this. So what do you do for functions of two variables?
We will find the gradient cell.
Okay, that is the
the
gradient.
partial derivatives.
Partial.
Using partial derivatives.
So you will solve for gradient equal to 0 and then do what?
So we will project using projection.
I think we have to perform Hessian test.
Yeah, so the Hessian
matrix.
right? So, but that we don't know. Okay, assume we don't know. We have done it in Max 2, but assume for now that we know till this. Okay, so we know gradient of f, we have to set it to 0, but after that we don't know. So this will only give us the critical points, right? So whether it's a minimum, maximum, or whether it's inconclusive, all that we can't say. Okay, so that's where this whole idea of quadratic forms, positive definiteness, all that comes in. So this is like a critical point, right? So critical point means gradient is 0. That much is clear, right, to everyone?
Yes.
Gradient of effort. Okay. So in week 2, we studied Taylor series. Correct? So we studied Taylor series expansion. Do you all remember that week 2? Week 2 or
Yes.
week 3? Week 2,
Yes.
right?
Yes, sir.
So if you expand a function of two variables around x star, you will get some terms, right? What is the first term?
F of x
Okay, f of x star. Okay, that is the first term. What will be the second term?
plus eta times d f eta times d f f dash of x star
Okay, so it's
plus eta square d square f double dash of x star up to so on by 2 factorial up to so on.
okay, that is for a function of one variable. So what is it for a function of two variables?
Dou f by dou x at x.
Okay,
Then
the third term. Okay, so revisit this part. So revisit Taylor series for a function of two
It will
variables.
be f of x and x1 and y1 is equal to f of x naught y naught minus eta times gradient of x naught y naught.
Yeah, so your gradient will come in, and there will be one more term. So this is like a second order term, which is the
Yes, sir. F double dash F double dash F double dash x we'll find double derivative and divide by 2
no,
factorial.
yeah, that's what I'm coming, right? So that is not as simple as finding the double derivative. It's you will have to find a matrix of second order partial derivatives, right? So I'll just put it myself. So you have f of x star plus h, right? So you're expanding it around x star. So first term will be f of x star itself. Then you will have the gradient coming in. So that's the first vector of first derivatives, partial derivatives. Then you will have, this is a matrix, right? So if you remember from max 2, this is your Hessian,
yes, sir.
right? So this is like del square f by del x square, del f, del x, del y, all that, right? So this is where if you what is this? H transpose matrix H. That is a quadratic form, right? So that is where the quadratic form actually makes an appearance. So what will happen to this equation? This will become, this term will become what? 0. Why will this term become 0?
Because every critical point.
Critical point, right? So this will become 0. So what we are left with is, this is Taylor series. So you are left with this. So I'm just taken f of x star to the other side. So you can describe this difference as half into h transpose h into h. So I'm calling this h. So what is this? Can someone tell me the meaning of this expression?
Change in x, change in f.
Change in f. Yeah. So if I move by some small distance, or if I move in the direction h away from x star, by how much does the function's value change? The function's value changes by this much, and you are giving that in terms of this expression, this quadratic form. Okay. So this quadratic, this matrix here is nothing but this thing. Okay. Second order derivatives, partial derivatives. So what is special about this matrix?
It's symmetric.
Right. So that's the most important thing. So you now see that this whole positive definiteness, quadratic forms, all of them, the reason they deal with symmetric matrices is, one of the reasons is this, right? So you are interested in the symmetric matrix and this quadratic function that involves this symmetric matrix, and that is somehow capturing the function's change in the function's value when you move slightly away from the critical point. Okay, I hope you are somewhat clear about this slide.
Then this matrix should be symmetric if and only if the function is continuous. Otherwise,
Yeah, right. That is that. So you should have continuous second order derivatives. Only then these are equal. as we'll assume that that happens, right? So we have continuous partial derivatives, second order derivatives. Okay, so this is called the Hessian. So very soon we'll get rid of this. So yeah, this is that, right? So is everyone clear with this equation on the right hand side? Expression half into H transpose H into H. This is fine, right?
What is H? H is a Hessian matrix.
Yeah, this I'm just replacing this big thing with H, del square. So we had del square here, right? So I'm just calling that H.
Yes.
Okay. So now what happens to F if we move in the direction H from X star? So if X star is to be a minimum, what can you tell me about this quantity? What should this quantity be? Should it be positive? Should it be negative? Should it be zero?
So it should be
Sir, 0 or greater than 0. Because
It should be
positive.
there should be some plus H.
correct. So it should be positive, right? So if you want this to be a minimum, this quantity should be positive, right? In fact, you are going to put this the other way. So if H transpose H is greater than 0 for all H, then what can you say about X star? X star is a
minimum.
And here it is maximum, right? So are you all able to visualize this? So this is like something like this, right? So, but then in 3 dimensions. So as you move away from this point on any direction, this right hand side is always positive. So when that happens, X star has to be the bottom of a bowl, okay, of a convex bowl. If when you move in this direction H, if this is negative, always negative, then what you are sloping down. So this is like an inverted bowl. In this case, it looks something like this. In this case, it looks something like this. Okay, of course, in 3 dimensions. Okay.
So once, could you please show the last slide? Yes, okay, thank you, sir.
Okay, so now we go to, so that is the motivation. So if you didn't understand this, it's okay. But I just want you to know that where this arises. Okay, so that brings us to a definite matrix. So matrix is symmetric matrix, right? It's always symmetric. So it's called positive definitive. X transpose AX is greater than 0 for all non-zero X. So why do we use non-zero here? If X is 0, what will happen?
Because X transpose AX is greater than 0.
Yeah, so it will be 0 then. So we ignore the 0 part. We are only interested in X transpose AX. It's the value of it, sign of it for all non-zero X.
It's strictly saying greater than.
Yeah. So this is positive definite. Okay, so this is positive definite. There are 5 things actually so far with respect to definiteness. So these are the conditions. So you could either have definite, semi-definite, negative, semi-definite. Okay. So the conditions are quite straightforward. So this is strictly greater than 0, greater than or equal to 0, less than 0, and less than or equal to 0. If it is none of these, it's indefinite. Okay. So that's the classification for definite matrices. Okay, is this clear?
What do you mean by none of this? Because anyways, it will fall under one of the category, right?
So it could be greater than 0 for some X and less than 0 for some X, right? So
okay.
In that case, it will be indefinite.
Okay.
Okay, so that is indefinite case. So that in fact corresponds to what is called a saddle point. So if you can visualize the horse's saddle, some direction it'll actually increase, some direction it will decrease. So that would be the case where if you move in some directions, it will be greater than 0. In few other directions, it will be less than 0. Okay, so that is a definite. These are the definite matrices, the definite and semi-definite. Okay, so there are 2 alternative definitions which are very important. So the first one is, in fact, a test for definiteness. So symmetric matrix is positive semi-definite. Okay, so another mistake. So this should be positive definite. Okay, so I have to update this. So erase the S out of this. These are all PD, not PSD. Okay, so a symmetric matrix is positive definite if and only if all its eigenvalues are positive. Okay, So that is one way to find out. So if you are given a positive, if you're given a matrix, symmetric matrix, and if they ask you if it's positive definite or not, first thing you do is find the eigenvalues. If they are positive, it is PD. Okay, so that's one test. The other test is actually very interesting. It's what it says is a symmetric matrix is positive definite again, once again, not S. If and only if you can write it as something transpose something. Okay, so if A is some B transpose B, then A is positive definite. In fact, if and only if it happens is A positive definite. Okay, so if you go back to SVD, what can you say about the matrices A transpose A and A transpose? They are what kind of matrices?
Symmetric.
They are symmetric, but based on your understanding of this, what can you conclude? They are also
Positive definite.
yes, so positive semi-definite, right? So there's small catch there. So there are, if the eigenvalues are 0, then you have to, strictly speaking, call it positive semi-definite. Okay. So A transpose A and A transpose are positive semi-definite matrices. So what about your covariance matrix, which you study in week 7? That is what? XX transpose by N, right? So what is that? That is also a
Positive semi.
Semi-definite.
that is also positive semi-definite. In fact, there is all the more reason to be positive semi-definite because the eigenvalues of covariance matrix, right? So what are they actually? They measure what? The variance, right?
So variance.
The eigenvalues of the covariance matrix, they measure variance in the principal directions. Therefore, they have to be positive or non-negative, right? So you once again see that positive semi-definite makes an appearance there. So these are two places. In fact, it makes one more appearance in a week that we have already studied. Can you go back to week 4? Where did you see a positive semi-definite matrix in week 4? You saw it in one place. Do you all remember when you were studying regression, right? Do you have any idea where we saw a positive semi-definite matrix there?
The projection matrix.
Exactly. So PP transpose, so that was one. So projection matrix was one. One more place. Very close to the projection matrix was the least square system, right? So you are trying to solve A transpose A x equal to A transpose B. So the A transpose A on the left was another positive semi-definite
It's
matrix.
10 o'clock.
Okay, so these turn up in multiple places, so make a note of it. Right, so that is PD. So all these definitions, if you change positive to non-negative, you will get PSD. Okay, likewise. Okay, so here it's fine. So this is fine. But here, if you change positive to non-negative, you will get PSD. Okay, is it clear? Can I move on? Few more slides only. So yeah, so that brings us to the quadratic form. Okay, so whatever we have seen so far are symmetric, positive, definite, or semi-definite matrices. But what we studied earlier, right? This whole H transpose HH, right? This is the motivation, right? So this thing is called a quadratic form. So why is it called a quadratic form? Can someone tell me where the quadratic comes from?
Say square of x is, I think, involved here, no?
Where is it?
Degree of equation is at most 2.
Yeah, right. So exactly 2, in fact, right? So in fact, every term is having degree 2. So it's of the form sigma I equal to 1 to n, j equal to 1 to n, aij, xi, xj, right? So you will have degree 2 for every term. So that's why it's called a quadratic form. Okay. So now we'll quickly look at quadratic forms in 2 variables, how to characterize all sorts of quadratic forms. So first thing is the matrix you start with is symmetric. Okay, so f of x is x transpose ax. So if you expand this, this will be x1, x2, a, b, c, x1, x2. So if you multiply them, this is what you get. So there's a very simple way to read off quadratic form. So the diagonal entries make up the coefficients of the pure square terms, right? So x1 square will have A, x2 square will have C, okay? And the off diagonal entries, if you sum them, they will be the coefficients for the cross terms, right? x1, x2 is a cross term. So 2b, x1, x2. Okay, so is this clear? How do you how do you connect a quadratic form and a symmetric matrix? Okay, likewise, you can. So yeah, so this is just a visualization. So what exactly is a quadratic form? So depending on the type of or whether it's positive definite or positive semi-definite or indefinite, whatever it is, the shape will change. So in this case, you have a positive definite quadratic form. So meaning A is positive definite. Okay. Therefore, you will have a bowl-shaped convex bowl, right? So where the minimum is at 0, 0, but everywhere else the function is, you can see, increases away from 0, 0. Okay. So in fact, this is what you want, right? So if you go back, if you want a minimum, if you want to characterize a minimum, you want H transpose HH to be greater than 0 as you go away from X star. Okay. So that's what is happening here. So as you go away from 0, 0, the function is increasing, right? So this is a positive definite case. This is somewhat an indefinite case, right? So if you actually zoom in, you will see that in one direction it increases, another direction it decreases. So this is a classic example of an indefinite case. Okay, this is just for visualization, right? What exactly these quadratic forms look like. So that brings us to this exact thing we were discussing, right? So quadratic forms and PD. So how do you know if a quadratic form is positive definite or not? What tests can you do? So what have I done here? Can someone tell me what I have done here?
Determinant.
Determinants.
Okay, determinant of what?
Matrix.
Matrix.
Equation.
Determinant of the given matrix A minus lambda, B, C minus lambda.
Okay, so it's the characteristic polynomial, right? So this is, I'm trying to find the eigenvalues of A, because if you want to find out if a matrix is positive definite, what did I tell you? You have to look at the eigenvalues, right? So the eigenvalues will tell you whether it's positive definite or not. So find the eigenvalues. So you have to do A minus lambda I. That's what I have done here, determinant. So if you solve this, you will get, of course, the eigenvalues, but then what are the conditions under which this will be positive definite? Lambda 1 should be greater than 0,
Greater than 0.
greater than, right?
Lambda 1 and lambda 2 should be greater than 0, strictly greater than 0.
Okay, so what are the sum of the roots? So sum of the roots are lambda 1 plus lambda 2, that is equal to,
Trace.
okay, what is it here? A plus C, right?
A
So A plus
minus
C should be positive. So A plus C should be positive. What is the product of lambda 1 and lambda 2?
determinant.
Okay, so that should also be positive. So you have two conditions. So A plus C is positive.
Yes.
AC minus B square is positive. This can happen only if, you can see that this can happen only if A is positive and AC minus B square is positive, right? So is this what sir also does in the lectures? Can someone confirm? If you have watched the lectures like thoroughly, for a quadratic form in two variables, is this the condition for positive definiteness that sir has mentioned?
Yes, sir.
You're sure, right? So can you quickly confirm with the slides?
So actually, I can't confirm, but yeah, I have seen this kind of.
Okay, yeah. So let me quickly, since this revision session, I'll quickly confirm. I don't want to.
No. I have seen in the videos.
Yeah, but you remember, right? So
Yeah, in video lecture.
Yeah, yes, sir. It's also for positive definite as a matrix should have the first value. A should be greater than 0 and the determinant also should be greater than 0, sir.
okay, yeah, okay. So this is, I think he has done it using a slightly different way, but that's fine. Okay, so yeah, that is there for PD. Okay, so that is PD. Three variables. So I'll quickly do this three variable part also. So X transpose AX. So how do you determine what goes into these equations, again, the same logic. So you look at the diagonals. So the diagonals take the coefficients of pure square terms, right? So ABC. And then this 2D, right? So how do you determine that this 2D has to be x1, x2? Because first row, second row corresponds to x1 and x2. So these two will go to determine
X1, X2.
and E will go to determine 2E will be x2, x3 because that's like second row, third row, second column, third column, and 2F for x3, x2. Okay, so that is 3 variables, and that's the last slide. So see, every quadratic form is uniquely associated with a symmetric matrix. Okay, you have to remember that. But this is not the only matrix, right? So you can have infinitely many A for which you will get the same quadratic form. Okay, so quickly I'll do that part alone and we can close. So you have, for example,
So
consider
actually, some questions are there like determinant and trace was given, and we have to find for the lambdas that kind of sub questions.
determinant and trace. Okay. Just a second. So this is like, this is one. Okay, this is one matrix. Let me put this as 4. So can you tell me the symmetric matrix associated with this quadratic form? What will it be?
2, 5, 5
Okay.
in the -2, -2.
-2, -2. Okay, can you tell me another matrix which is not symmetric, which will go into the same, which will give you the same quadratic form?
2, 5, 0, -4.
0, -4. Okay, so notice that this is not unique. Okay, so the A is not unique. If you express this as xy, so xy A xy, right? So or rather this is what xy, whatever this is, right? This is some A and then column vector xy. So this A is not unique, but then moment you say that A is symmetric, it becomes unique. Okay, so you are forced to come up with, this is the only symmetric matrix which will give you this quadratic form. Okay, is that clear? So is that clear to everyone what I just said? Okay, therefore you can say that the set of all quadratic forms is equivalent to, not equivalent, so is, how can I, what do I say? So can be, okay, I'll put it this way, can be put into one-to-one correspondence with the set of all what? Symmetric matrices, right?
Matrices, yeah.
So for every, that means what? For every symmetric matrix, I can find a quadratic form. I can find a unique quadratic form, right? So that is the catch. This unique is important. Likewise, I can flip this.
So matrix A 2, 0, -4, 5 is not symmetric, sir? Oh, well, this is,
Yeah, this is not symmetric, right?
oh.
Yeah, so I hope that is clear. So I can reverse this, right? So for every quadratic form, I can find a unique symmetric matrix. So this is important. Okay, so this relationship between the two is important. And yeah, so I think I've kind of not explained this part quite well. So I have only shown you what is the relationship between quadratic forms and positive definiteness, but I think the lectures sir has covered the conditions for negative, definite, semi-definite also. So maybe I will update that later. But for now, right? So what I would suggest is, instead of going through this determinant, this A greater than 0, AC minus B squared, it's a bit cumbersome. So whenever you are asked about quadratic forms and positive definiteness, always go for property number 1. Okay, what is property number 1?
Eigenvalues, yeah.
Right, so this is cleanest because this will always work. So if the eigenvalues are positive, then it's a PD. Okay, not PSD, PD. There there are no second thoughts or no doubts about this. Okay, so this AC minus B square business is fine, but that's only that you can only do that for 2 cross 2, right? For higher order matrices, there is something similar. It's called the Sylvester's criterion, but that we have not covered in this course.
Sir, if any of the eigenvalues is 0, then it will be positive semi-definite.
Provided all the others are positive, right? So if it is greater than or equal to 0, it's positive semi-definite.
No. Like in the exam, we have any 3 by 3 matrix, and they are asked, okay, it is say positive semi-definite or positive definite. Then we'll check for eigenvalues, and if one of the eigenvalues is 0, then it is positive semi-definite.
Correct. Yeah. Even if there is even one 0 eigenvalue, it becomes positive semi-definite.
Yes, for positive definite, there should be all the eigenvalues non-zero.
Yeah, all eigenvalues have to be non-zero. For positive definite, all eigenvalues are positive. Okay. So yeah, that is.
So, what if we are given a quadratic equation and we are meant to check for this condition? Can we convert into any matrix and then check the eigenvalues? Will that work?
Yeah, that will work. So for example, this itself, right? So if you're asked a question like, oh, if this is a question, right? So consider the quadratic form f of xy is, okay, is this positive definite? So if this is a question, then what you do is there is only one matrix, as I said, you can associate with this, right? So this is 2 phi minus 2 minus 2, right? This is the only matrix you can associate with this, because only for symmetric matrices is this whole idea of positive definiteness even defined, right? So the steps you'll do, first thing you'll do is step 1 is find D, right? Because there's only one such matrix. Find the symmetric matrix. Step 2 is compute the eigenvalues of A, and then look at the sign and determine if it is PD or not.
Okay. What I thought was like we can always construct a lower triangular or upper triangular matrix, and then we can get the diagonals, right?
That is also a good idea. You could do that. For example,
Yeah. Earlier we discussed 0 minus 4. So we'll be getting 2 phi as the eigenvalues.
yeah, so 0. Yeah, I suppose you could. Let me think 1 second. This is a good. That's a good suggestion. Will we run into any? 1 second. Wait. Hold on. So X transpose AX. The quadratic form. So when is the quadratic form positive definite? Whenever f of xy is greater than 0 for any xy not equal to 0, right? So if you define it as, for convenience, I'll just use x, right? So X transpose AX, and you say X transpose AX is greater than 0. Okay, so what you're saying is, so we want to check whether the function is positive definite, right?
Yeah.
So we want to, let me just write it down. We want to check whether f of x is greater than 0 for all x not 2, where x not equal to 0. So this is what we want to check. So f of x is, so this is what X transpose AX. So now we are saying A is not symmetric. Okay, so A is not symmetric, and A transpose AX is 0, greater than 0. Now, so if X transpose AX is greater than 0, this is what we have to check. Now, if you do it for, see, the problem is, if A is not symmetric and you want to show, see what I'll just first write down what you're saying, right? So A is not symmetric, that's number one. And what you're suggesting is A is upper triangular or lower triangular. I'll take upper triangular. And then you are saying if the eigenvalues, let me know if this is what you're saying. If the eigenvalues of A are positive, then f of x is PD. Is this what you're saying?
Yes, sir.
Okay, so if you want to show that x transpose AX is always greater than 0, so what I'm worried about is, see, if you go back to this proof, right? The proof for positive definite involves only the, so one direction, it involves only the eigenvalues. If A is positive definite, then that is okay. But what I'm worried about is if A is not symmetric, what will happen? So it's a good question. Okay, so I don't know the answer right away, but I will. Do you use discourse?
Yeah.
Okay, just I will tag you. So I don't know what your ID is. Can you post your ID here in the chat? I'll
Yes, sir.
tag you so that I'll create a post and tag you there. So I just need to be a bit careful before I confirm or deny this, because this seems like a very good observation, but I'm not able to say for sure if this is right. Yeah. Okay, so that's a good question. I'll get back to you on this.
Yes.
Any other questions?
If we can construct a symmetric matrix, then we are guaranteed if we are checking that condition, right?
Yeah, if you can construct a symmetric matrix, then you are done. So then there is no question of, there's no confusion there. If it is per triangular, does the same conclusion hold? I don't know, because see, if it is symmetric, you can use the, so for one thing, right? So first of all, let's see why this is true, right? So if you have, I put this below. So you want to test whether x transpose AX is always greater than 0, right? So if A is symmetric, then I can write down A as lambda 1 V1 transpose plus dot 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 plus lambda n. So in this case, it's R2, right? So I can write this as lambda 2 V2 transpose. This comes from spectral theorem, right? So A is Q D Q transpose. So Q is 2 cross 2, D is 2 cross 2. There are two eigenvalues. And the eigenvalues are, so these are the eigenvalues, right? So if the eigenvalues are positive, okay, so what will happen is x transpose AX will always be positive. So how do you show that? So this part you understood, right? Why we can write A as this?
Yep.
So you can write A as this. Okay, so if A is symmetric, so if A is symmetric, then I can do the spectral decomposition and A becomes this. So far we don't know whether it's positive or not. So that's what we want to show. So now I can, since V1 and V2 are orthogonal, this forms a basis for R2, right? So I can express any x as some alpha 1 V1 plus alpha 2 V2. Are you convinced about this part? It's like expressing it in terms of the basis V1.
Yeah. Okay.
Okay. So now if you take x transpose AX, so this is what? This is nothing but alpha 1 V1 plus alpha 2 V2, alpha 2 V2 transpose this whole thing. So this A1, this lambda 1 business, this one, and then you'll have this one again. So this is what you'll have. Okay. So now you can actually expand this, right? So the orthogonality helps us a lot. So if you actually expand this, let's keep this as it is. Sorry, as it is. So if you expand this, you will notice that lambda 1 v1 v1 transpose will clash with v2 and become 0.
Yeah.
We will be left with what? Lambda 1 v1 alpha 1, correct? So alpha 1 lambda 1 v1 plus alpha 2 lambda 2 v2. Is that correct? Because they are
Yes,
unit. They are unit norm, right? So v1 transpose v1 will collapse.
Yeah.
You will be left with alpha 1 lambda 1 v1 and alpha 2 lambda 2 v2, correct?
Yeah.
So now if you take the transpose once again, so you will be left with alpha 1 square and v1 transpose v1. So you'll have lambda 1 v1 plus alpha 2 square lambda 2 v2, correct?
Yeah. Okay.
Right? So this v1 v2 again it will collapse. So there will be a square. Okay.
Yeah.
So this is x transpose ax. Now, why does this help? So if lambda 1 is greater than 0 and lambda 2 is greater than 0, then notice that x transpose ax is greater than 0 for all x in R2, right? All non-zero x in R2. Because this is positive. Lambda 1 is positive. Okay, wait, once again. This is I made a mistake. So this v1 will not be there. Correct. So this v1 transpose
Yeah,
v1.
correct. Yeah.
So,
Okay.
so this is scalar. So this is scalar. So this thing will, if lambda 1 and lambda 2 are positive, then x transpose ax has to be positive for all x in R2. Okay. So that's how we show that. So what have we shown? If, so this started right here, right? So if A is symmetric, then, so sorry, this whole thing actually goes on to show that if A is,
not
if A has positive eigenvalues, right? So that's what we have shown. So if A has positive eigenvalues,
And A is symmetric.
yeah, if and A is symmetric, if A is symmetric and symmetric with positive eigenvalues, then x transpose ax, f of x equal to x transpose ax is PD. So it's always greater than 0, PD, right? So that's what, so that is what we have shown. So this is fine. So this is one direction. The other direction is very clear. So if the matrix is positive definite, then so if f of x is positive definite, then eigenvalues are positive. It's not very hard. But what we want is, given a function, that is what you wanted, right? What did you?
Given the-
Again, it is showing symmetric, and that his question was not symmetric, right?
Yeah. So that is the question. Now, okay. So this is the proof for showing that if it is symmetric, then we can show that it's positive definite. Now the problem is, if A is not symmetric, I don't
can't
know.
construct any of these, right?
Yeah, that's the problem, right? So this argument breaks down because it breaks down here itself. So yeah, so that is where you will have a problem.
Okay.
Yeah, but I haven't, at least I haven't shown you still. I need to present a counter example. Only then can I say that your argument is wrong. Until then, I can't say conclusively that this is wrong. So yeah, so I'll get back to you. Okay, so this part is, I have made a note. So okay, any other question? If anyone else has? Not, we'll close it for now, and we can meet again soon.
So is he saying about like converting matrix to like doing LU decomposition of a matrix, then checking for eigenvalues?
No, so see, the point is, if you are given f of x, right? So if you are given this, then this is the question, right? We want to answer this question. If you are given a function, can you tell me if it is positive definite, meaning x transpose ax should be always greater than 0? How is this the case or not? So you could, what we have been saying so far is find the symmetric matrix A corresponding to this and check its eigenvalues. If it is positive, then this is also positive, right? So that's one way of doing it. Now, the question is, can we come with some other matrix A which corresponds to the same quadratic form, for which it's easier to compute the eigenvalues, like upper triangular, right? So upper triangular would be 2, 5, minus 4, 0, right? So this is also the same quadratic form. And I know that the eigenvalues here are positive because I can read them off the diagonals. Does that mean I can conclude that this is like positive definite? Right? So that is the question here. See, in fact, you can take this example. Say, make this 10. Okay, so make this. If you make this 10, what will happen? The eigenvalues are positive, correct?
Yes, sir.
Eigenvalues are positive. But if you look at the corresponding symmetric matrix, right? So this is like, let's call it A prime. So this is X transpose A prime X, this is X transpose AX, right? So where A is symmetric, A prime is not. So A will be what? 2 minus 4. Sorry, 2, 10, minus 2, minus 2, correct? So what are the eigenvalues of this? This is 2 minus lambda. Sorry, so 2 minus lambda into
10 minus lambda
minus lambda plus minus 4, right?
Yeah.
minus 4.
So this is lambda square minus 12 lambda, correct? Plus 20 minus 4 plus 16, correct? Let me know if this is correct. Sorry. Is this correct so far?
Yes, sir.
So what do you get? Lambda is 4. So it's like, I don't think we can directly solve. So plus or minus root of. So I want to see if they're positive or not. So it's 144 minus 64, right?
Yeah.
By 2. So quickly, what is this? 12 plus or minus
Root 80.
80, yeah?
Yeah.
80 by 2. So approximately what is root 80?
9.
9. Okay, so 12 plus or minus 9. Okay, unfortunately or fortunately, this is positive, right? Both are positive. So you can't conclude. So in this case, it seems to work. For whatever example we have taken. So what we need is a negative determinant. If we can find a negative determinant, we can say that. So hey, can you give me 1 minute? Just 1 minute.
Yeah.
Sorry. So if you want, see, the product of eigenvalues is the determinant, right? So if you want your determinant to be negative, how should you change this? I don't want to change minus 4.
We can take minus 2 or minus 10.
Here, minus 10.
No, like x square or y square coefficients.
But then, so see, the point is I want the diagonals to be positive. So the eigenvalues, I want them to be positive. Okay, then there is no, like, I will always get the positive determinant, right? Because eigenvalues are. Okay, so yeah, so this is slightly trickier than what I thought. Positive eigenvalues. Yeah, so this, yeah, Girish, I will get back to you, right? So this is not, doesn't seem.
But one intuitive idea I have is x. We can take x square minus 100xy plus y square.
Okay.
We can make this to be very big and this to be small. And by looking at it, at some point this function will definitely come negative, right? Because b term is very large. We will be subtracting more quantities.
Yeah, that makes sense. So we'll just write out. So this is minus 100. So yeah, in fact, you can make this in fact huge, right? If you blow this up to like 10 power 10 or something like that, this will, yeah, you are right. Yeah, this has to be, so this will become minus 50, and you are bound to end up with something. Yeah, that is correct. So you are going to get, so even though the eigenvalues are positive for A prime.
So in the equation you removed 10, the coefficient of y square. In the question.
So it becomes 1.
Yes, here
Or,
it should be 10 square.
In what
10 y
was
square.
it? It was 10, right?
Yes.
Sorry, I let it be 10. In fact, yeah, it can be simpler, right? So it now need not be so complex. So it can be simpler.
this
So,
one, yeah.
so 1 and minus 100. So it can be, in fact, at 1 comma 1 itself, this is negative, right?
Yeah.
So at 1 comma 1, this is negative. However,
Like 1 minus lambda into 1 minus lambda minus plus 100.
yeah. So that would be, so yeah, I think that is the answer to the question. Yeah, you are right. So you can have this as minus 50, 1, 1, and this would be 1 minus lambda square. So this is like 1 minus lambda square minus
Plus
50 square.
Minus.
minus 50 square.
Minus
Yes.
50 square, right? So lambda would turn out to be, so this is plus or minus 50, 1 plus or minus 50, correct?
Yeah.
Yeah, so,
Okay.
so that is, I think that is the answer. That is the reason. Or rather, this is a counter example to show that
This won't work.
Yeah,
We
this-
should always rely on the symmetric.
matrix, yeah.
Okay.
Yeah, but this is a very good question. So it's a very good question. And we had to dig into some counter examples to get it. Yeah. Okay. Any other questions? If not, we can close.
No, sir. It was a good session. Thank you, sir.
Thank you. Yeah. So thanks everyone. All the best for your exam. So mostly I'll be meeting you for week 9 directly. Okay.
Thank you, sir.
Thank you, sir.
Thanks.
Thank you, sir.